Microtrac would like to thank you for viewing this on-demand presentation. Some of you may be familiar with the Microtrac brand. We have built a stellar reputation for delivering particle characterization solutions since 1972. Last year, we began to offer surface area instrumentation by forming a strategic partnership with our sister company, Bell Japan. I would like to take this opportunity to introduce you to our speaker, Dr. Phil Plantz, Microtrac's application manager. Dr. Plantz has received his master's and PhD from Penn State University. Dr. Plantz has over 30 years of experience in material characterization and also works as an adjunct professor at St. Petersburg College in Florida. Now I would like to introduce you to today's agenda.
First, we're going to introduce you to surface area. For some of you, this may be a refresher. For others, this will be a great learning opportunity. Key terms such as the difference between Kemahsorption and Adsorption, applications such as Z-life, ethanol separation. We will also take a deeper look into our patented approach to improving measurement efficiency by correcting dead volume. This approach is called AFSM. Next, we will look at how to express isotherms and what information you can gain from them. And we will also look at the Bell product line. And then we will wrap up with Q&A. We will also have Kate Tsuji, the Bell Japan product manager, available as well to answer any questions that Dr. Plantz may not be able to. I ask you that you please hold your questions until the end of Dr. Plantz's presentation. And now I hand it over to Dr. Plantz.
Good afternoon, everyone. Thank you very much for joining us this afternoon on your computers, your iPads, and your smartphones on this very important topic of surface area measurements, and in particular the Bell instruments. What we have before us is the Milky Way galaxy, and there's our Earth as part of the Milky Way galaxy as we view it from interstellar space. But as we start to approach our Earth and get closer and closer to Earth, we start to realize that this object we call Earth appears to be a nice round spherical ball. But as we start to get closer and closer to our Earth, and in particular if we look up in this area of the United States, and if we go closer in to the United States, we can notice out here in the western part the Rocky Mountains and other topographical aspects of our country. But as we zoom in even closer into that area, we start to see that there's a lot of features that are not evident when we're looking at this orb we call Earth from space. And it's comprised of mountains and valleys, plateaus, caves, volcanoes, and as a last type of topographical object, we have these buildings. So Earth isn't really a nice, smooth place to try to do surface area measurements. So if we were to try to measure the area, the actual surface area of Earth, it really can't be measured because there's so many changes, and peaks and valleys, and literally holes in our Earth. But when it comes to particles, we can make that measurement, and that's because they are much smaller, and we can perform certain tests that are not possible on Earth. The general surface of a particle by many particle-size measurements would provide us with some type of an outline or equivalent spherical diameter. But when we start to look at surface area, there are many features that really add to that surface area, and these can be particles that have objects or pieces that are removed or never solidified inside the particle. And these can cause voids in terms of cylinders, slits, cracks, hills, peaks. And the primary method for making this measurement is using nitrogen. Krypton, argon, and various other gases and water vapor can be used. Now these various types of pore structures are comprised of four main shapes. One of them is a cylinder, and for the purposes of surface area, this includes also what's called a funnel as well as a bottleneck. And these three are considered to be a cylinder. And this is similar to drilling a hole into a surface or into a board or something of that nature. The other type that starts to be considered is this constructive here, which is a slit. So it's important to have some idea of the structure of these voids that exists in a particle. Now, one other thing I do want to point out to you is this area right here where we have closed pores. Now, you'll notice in this particle there are many, I'm going to call them holes just to make a general term, but these holes in the particle here, these represent closed pores. These do not have an opening to the surface of the particle, so these voids do not become part of any surface area measurement. But on the other hand, all the rest of these surface characteristics that I'm outlining with my pointer do have an opening where the absorbing gas can enter and start to give us information about the total surface area that's available for various chemical means, purification, and other aspects of using materials. Just as a little bit of history, when we look at the science of surface area measurement, it dates back all the way to 1773, and through a number of years we finally come up to about the 1920s, 1930s, when various scientists started taking a look at the systematization of surface area measurement as a true science. It turns out, though, that in ancient China and Egypt, there were actually adsorption concepts being used, although they didn't understand the chemistry or the physics behind those measurements. The Egyptians used it to decolor various types of drinks. Chinese, in 1971, there was an exploration, and they found a body that had been preserved in almost its perfect state by use of packing the corpse with carbon black. So the whole concept of using adsorption concepts and its practicalities date back many, many years. Now, in our recent time, particularly in the last 70, 80 years, there were many industries that have become involved in the use of adsorption concepts, and that involves the energy business, the energy market segment, the petrochemical area for fluid cracking catalysts and other types of catalysts, gas purification and separation, the use of various adsorbents and manufacture and development of those materials, as well as environmental concerns, the green concepts involving climate change, where we have carbon capture and storage, and also the whole area of catalysts. In particular, these industries are using or manufacturing various types of porous materials such as zeolite, activated carbons, PCP, and carbon nanotubes. And we can see over here to the left, where we have a structure of carbon nanotubes, that this is a very open structure, and it has a tremendous amount of surface that's available for various types of adsorption and various types of chemistry that might be applied by using carbon nanotubes. Now let's stop and sit back for a second and think about some definitions so that we all get on the same page. The concept or the term absorption includes adsorption and absorption. Adsorption, the AD adsorption, this is where a gas or a liquid will accumulate on the surface of a solid. More rarely it might be a molecular or an atomic type film. On the other hand, the absorption is where a fluid permeates or is dissolved by a fluid, or it can be absorbed into a particular solid, much as what you may find by using a sponge. The whole concept with adsorption is that if we provide an interface between a gas and a liquid, these gas molecules sitting out here to the left, due to their normal kinetic activity and motion and velocities, will strike the interface. And some of these molecules can be adsorbed or stick to that interface. Others will be removed. When we look at adsorption, we'll see that these molecules can pass into the solid. And just to give this a little bit of a different view, we can look at our chubby little friend over here, and while he wants to eat this pie and consume it and absorb it into his body, the other type would be adsorption, where he kind of gets hit with the pie, and the next thing he knows, he's covered with that pie and its contents, and it's on the surface. So this poor fellow with the pie in his face is considered adsorption, and this fellow over here, where he's eating the pie, would be considered absorption because it's entering the substance rather than just remaining on the surface. Further, with some definitions, the first word that's important is the concept of a molecule being an adsorptive. This is a molecule that's floating around near our particle surface, and our particle surface has the terminology being an adsorbent, and this molecule is not yet adsorbed. But as we go through the adsorption process, we see that molecules can contact the surface, and they will become attached to the particle surface, and once they become attached to the particle surface, we will call that the adsorbate. And again, this is the gas that's actually adsorbed to the surface. Now, another part of the process that we're going to be looking at is the desorption process. And both adsorption and desorption provide for a full isotherm evaluation of the particles in terms of its surface area and some other characteristics and its pore structure. Now, dividing this absorption concepts and adsorption and desorption a little bit more, what we can do is look at what's called physisorption, and we'll compare it to what is called Kemahsorption. With physisorption, when the gas molecules attach themselves to the surface of the particles, it's a very weak adsorption phenomenon. No chemical bonds are being formed, and as a result, this process is reversible. So the adsorption process is reversible, and this reversible portion is called desorption. This provides us with the opportunity to measure surface area and obtain pore analysis as well. With Kemahsorption, the adsorption is very strong because chemical bonds are being formed, and under these conditions the process is irreversible. But this irreversibility provides us with the opportunity to understand better the surface properties and the chemistry of the surfaces, and this can include acid nature, basic nature, or caustic nature, the hydrophilicity or the hydrophobicity. Now, the whole process that we're really talking about, if we look at the diagram below, the adsorption process, if we start over here, under these conditions we have a very low concentration of the adsorbing molecules, and at this point no adsorption is occurring. But as we change the concentration of that adsorbing gas, or in other words, we're increasing the pressure of that gas associated with the material, molecules of the gas start to attach themselves to the surface in the pores and on the surface of the particle. But as we increase the pressure or increase the concentration of the adsorbing gas, more and more of these molecules attach themselves to the surface. At this point, these molecules are can still undergo desorption. Eventually what we do is wind up with a situation with this particle where the pores become completely filled with the adsorbing molecules, and this is now an adsorbate. But under these conditions, at this point, we can reverse this process, and we do this all isothermally. So the temperature is the same, and it's at 77 Kelvin, which is the boiling point of liquid nitrogen. But at this point, we can just reverse this process by reducing the pressure. So up until this point, we've done adsorption. Now we can go backwards and do the desorption measurement by reducing the pressure and the concentration of the gases, and we'll just follow the path back this way until we no longer have any molecules available for adsorption. Now, on the other hand, this is again a reversible process. On the other hand, we can follow the path through Kemahsorption, where the molecules again pile up, but the molecules in this case are really starting to attach themselves very strongly to the molecules. So as we start to reduce the pressures, molecules that have filled the pores now start to remove themselves from the surfaces, and as the concentration and the pressures decrease, the final result is that molecules that have reacted, chemically reacted with the surface, now line themselves on the particle and the interstices of the particles. So there is a difference in the final point of physisorption and the final point of Kemahsorption. There are a number of applications for surface area these days. If we just take a look at a couple of applications, the petrochemical industry, catalysts, cracking catalysts, exhaust gases. We'll look at this a little bit more in detail. Environmental issues with carbon capture and storage, the greenhouse gases, energy industry, storage and fuel cells. Fuel cells have been known to be used in space for quite some time. Carbon dioxide capture, water purification, ceramics, the nano sizes for aluminum, silicon, TiO2. And then down here, as I jump down, we can look at pharmaceuticals. And keep in mind that every time a particular drug or medication is taken, the whole purpose of that is to be absorbed by the body. That absorption rate is controlled by the particle size and the surface area of the particles. Now, if we look over here to the right, one of the things I want to note to you is that you'll see different names: Bell Bax, Bell Mini, Bell Cat, Bell Mass, Bell Metal. These are instruments. Max and Mini are general purpose instruments, but then as we get to the Cat, the Mass, and the Metal, and the other Bell products, these become more specific in nature, and Bell has those types of instruments available for very special types of analyses that would not be done by the Bell Max and the Bell Mini, and I'll explain to you the Bell Max and Bell Mini later on in this talk. But one thing down here, we had this Bell MR6. This is a single point BET measurement, and we'll talk a bit about BET. But this allows you to do 6 samples simultaneously to speed up lab measurements. Now we have this particle, whoops, sorry. We have this particle up here. Now this is a silicolite MFI, and this material, when we look at it under SEM, just like our Earth from space, we see that this particle looks very, very smooth, has no particular features associated with it, and looks like Earth from a long, long, long way away. But actually this particle does have a lot of structure. Now I've drawn a nitrogen molecule over here, and this is a diatomic molecule. Its shape, its size is on the order of 0.36 nanometers. So this allows us to make measurements of both micropores as well as mesopores. Now this structure for this particle shows the nitrogen molecules being absorbed in the surface. Here's a bottle neck pore. These represent cylinders, and over here we have a slit shape for the particle. And in fact, this particular material does have a lot of very high porosity associated with it, which is not evident from the SEM photograph. This is a material called MFI zeolite. MFI is a special structure that's been developed that's very useful in adsorption in a number of cases. Again, this is a SEM photograph, but this time it doesn't look so smooth, and it's got some roughness associated with it. So it's an indication that the surface area is not from a nice smooth surface. It's more bumpy, and those bumps give rise to a higher surface area. But we can see evidence that mesopores from 2 to 15 nanometers, and this is the mesopore range, are present. But there's no information about the micropores, which have a size of less than 2 nanometers. But it does have both. Now, one thing I want to point out with this type of a measurement, because of this special structure, and that special structure is shown down here, that argon is the gas of choice because it is a smaller molecule, and it will fit much better when the adsorption process is being performed. So adsorption plays a very large role in characterization. And again, when it comes to particle characterization, you can look at shape, you can look at particle size distributions, masses, a number of aspects, including chemical composition, when it comes to a full characterization of a material. Now, this application shows a membrane separation for ethanol. And what we have here is a photograph. This is a support material, and this support material is a zeolite. But right here, this support material could be alumina, it could be any number of different oxides. But right here on the surface, we see zeolite, and it has a thickness of about 18.4 microns. The whole purpose of this particular zeolite and this material is that the zeolite is being layered in a series of layers to allow purification of bioethanol that's obtained from sugarcane. Now, when the sugarcane is used, there's a number of impurities that are produced along with the ethanol. The zeolite membrane has the ability to remove all of those impurities, but it can only do that under certain conditions where the pore structure is of the right size and the correct amounts. Using the Bell instrument under a single condition of measuring both micropores and mesopores, and I'll explain a little bit more about that, we can see that down here below 2 nanometers, these pores, this does have a micropore structure. It also has a mesopore structure lying between 2 and 50 nanometers. And then there's some evidence of some macropores out here. This in the right-hand corner shows the actual stacking of these various membranes. And the whole purpose, again, is to remove contaminants. The ethanol can pass through this entire structure of these different layers while at the same time absorbing the contaminants, which allows for purification of the ethanol. There are a number of methods for using adsorption and performing adsorption. Early on, gravimetric was used. Today, very sensitive balances are being used, and the method here is that the material is subjected to the gas molecules, and the change in weight that occurs during that adsorption process is measured and monitored, and from that the surface area can be determined. In more general terms, the dynamic flow method. Here we'll have a mixture of gases, and this is flowed over the sample. The concentration of the gas, and this is usually nitrogen if someone is doing a BET surface area measurement, the concentration of gas before and after the exposure to the gas is determined using a thermal conductivity detector. The volume of gas desorbed that volume is used for the amount that's adsorbed according to the BET formula. This provides lower accuracy because of the technology that's involved, and it also requires special mixtures. Now, one thing, if there's a tank of gas that has a mixture of, say, 30% nitrogen and 70% helium, if that tank of that mixture is allowed to stand, those gases can demix and cause some real issues with doing the surface area measurement. It would be far better to have some type of a mixing valve or some other method for dealing with that. The volumetric method, this is where we have a powder, and it's placed in a sample container of an unknown volume, and it's exposed to a known volume of gas, and this is the absorptive gas. And the amount of gas adsorbed is determined by pressure changes. And the reason why we can determine the volume of gas that's adsorbed by using the pressure takes us down to what is called the ideal gas law. And here we have a relationship between pressure, volume, the number of moles of the gas constant, as well as the temperature. So there's a relationship between the pressure and the volume. And typically volume that we really are interested in using for calculations. This will provide very high accuracy and allows for pure gases to be applied, no demixing issues, and it requires an accurate void volume or errors can accumulate. And we'll talk about that void volume because that's an important aspect. In the Bell instruments, to deal with that void volume errors, what's called the advanced free space measurement is used. And we call this the AFSM method. And this brings us to the dead volume or the void volume. Now, the issue here is that when a sample tube is immersed in liquid nitrogen, the liquid nitrogen, because of its vapor pressure, will boil off at some rate unless it's prevented from doing that or constant refilling is performed. Now, that becomes important because typically in most instruments, that dead volume is measured before or after the adsorption measurement. But what is actually happening is that if this is our sample here in the bottom of this little sample tube, and if we fill the vessel that we're going to immerse the sample in to allow for its adsorption, remember, adsorption must occur at 77 K so that nitrogen molecules can condense on the surface of the sample particles. But if we fill the vessel to this level here at level 1, over a period of time and during the measurement, the liquid nitrogen will boil off as it will, and that level will drop. But as this level drops, the exposure of this gas to the liquid nitrogen is decreasing. As a result, there's a temperature change that's occurring, and that temperature change is going to affect the measurement of the pressure, which is related to the volume of gas that's actually being absorbed by the sample. So this is a great source of error, and there is a means around this that is very, very accurate. Rather than measuring the temperature after the measurement or before the measurement, or even taking an average of before and after, that still does not provide the high accuracy that many researchers and users require. The method that we use in the Bell instruments is this method we call the advanced free space measurement. Now, this is very similar to using a spectrophotometer, where you're trying to determine how much light is absorbed by a substance that's reacted in a solution. But we want to run a blank to make sure that any development of any spectrophotomic coloration or anything of that nature, if that were to develop, that would cause error in our measurement. So what's necessary is to use a blank. So this is very similar to using a blank. And anything that's happening to our sample over here, whether the liquid level drops during the measurement and this pressure is changing, that will happen also to our blank tube, where the pressure will drop to the same amount that's our sample's experiencing. So what we actually experience over here with our sample is pressure changes that are occurring as a result of adsorption by the sample, and also in addition is the change in the level of the liquid nitrogen. But we don't have to be concerned about that level changing at this point, because we're monitoring the pressure change due to the drop in the level of the liquid nitrogen. Thus, we take the pressure drop and, in effect, subtract it from the pressure that's being experienced in the sample tube. And then that gives us a very highly accurate measurement of the pressure and ultimately the volume. Adsorption is pretty much involved with the amount of nitrogen or other gas or vapors being adsorbed to surfaces. Keep in mind that the measurement's being done under constant temperature. The whole concept of constant temperature allows us to develop that term isotherm. Iso meaning same and therm temperature. What I'm showing you here is the volume of gas that's being adsorbed as a function of the relative pressure. So this represents the concentration of the adsorptive that's being applied to the system. But if we start right here, and just to let you know, this is typical of what's called a type 1 isotherm. And activated carbon has many micropores. This is indicative of a highly microporous structure. But as the relative pressure is increased, the gases are being absorbed very, very rapidly, and it will follow all the way out to the end of the adsorption isotherm. And then if we continue with desorption, we'll follow this path back here. And you'll notice that these two curves are superimposed. And under these conditions of a highly microporous material, that is pretty much what will happen. Now, I mentioned the concept of an isotherm, and this is what I just showed you is indicative of what's called a type 1 isotherm. There are type 2 isotherms, and each one of these isotherms has a characteristic shape. And under this condition here with this type 4 isotherm, we see that the adsorption isotherm takes on this type of a shape. But then during the desorption process does not follow the path of the adsorption. And this difference that's occurring is called hysteresis. And this is indicative of various types of mesopores. Then we have another type of isotherm over here, and you'll notice that the slope here is very, very gentle before it starts to increase in terms of the volume being adsorbed. This is indicative of materials that do not adsorb very readily, as opposed to our micropores, where the micropores are gobbling up those adsorptive gases at a very high rate. Type 6 is a very, very highly unique, very rare situation where there's a stepwise adsorption process that occurs. And one thing I do want to mention once again, whoops, get back there. One thing I do want to mention, micropores are 2 nanometers and smaller. Mesopores are 2 nanometers to 50 nanometers, and macropores are on the order of 50 nanometers and greater. Now what I have here is a fairly complex adsorption-desorption isotherm. And what we do is we start out here at the lowest state, and there's no adsorptive gas available for adsorption. But as we start to increase the relative pressure, then we start to see adsorption starting to take place by micropores. Now, I just want to note to you that in this range from 0.05 relative pressure out to a relative pressure of about 0.3 to 0.35 is the range of relative pressures where BET surface area measurements are made. But as we go beyond that 0.3 relative pressure, we get into a range where mesopores are being measured. And this is the mesopore range. So in this particular adsorption-desorption isotherm, we have the presence of micropores as well as mesopores. And here we're starting to experience multi-layer adsorption, and this is a key issue with development over the number of years with understanding adsorption phenomena in general. The last point of this is that the pores are completely filled and the surfaces are completely filled, and we have molecules attaching to molecules and molecules attaching themselves and adsorbing to the surfaces. This final point here can be used for calculation of the total pore volume and obtaining an average pore size. There are calculations available that I'll point out in a second, and as I did previously in the previous slide, where the distribution of the pore size is not just an average pore size, but a true distribution of the pore sizes present can be determined. Now, it's important to realize that as materials change, their chemistry, their surface chemistries, they can change as well. So adsorption phenomena is totally a matter of the state of the sample surface and the ability of the gas and the sample to interact favorably, and that's really gets into the surface energies and other aspects of surface chemistry. I'd mentioned to you just a second ago about the single layer of molecules forming on the surface. And keep in mind that throughout this process that these gas molecules can arrive at the surface and then they can just leave the surface spontaneously. But over a period of time, there will be a buildup of the gas molecules, the adsorptive, onto the surface. But as well, there can and is a buildup of other of the gas molecules on top of each other, so that there's a layering effect. This process, where there's the assumption that only one layer or a monolayer of molecules, gas molecules, exists on the surface, was defined by Langmuir, and after some tremendous analysis by Brunauer, Emmett, and Teller, the formula started to include the phenomena that gas molecules can attach themselves to other gas molecules, producing what's a layering effect. Down here at the bottom, the Langmuir assumes this type of adsorption occurring, which is not, in fact, the best science that can be applied. In this case, in some cases, Langmuir adsorption can be applied for Kemahsorption. In actuality, what is probably happening is something like this, and this is why the BET became very, very important, because it took into account the fact that molecules can layer themselves, and this has to be taken into account because the surface area calculations really should just be including this single monolayer of gases. So the BET formula, after you go through the derivations, will allow the formula that they've developed, and this can be put into the form of a straight line. And in general, for those of you in the research, you realize that being able to put data into a linear regression or something of that nature allows data calculations to be much easier. But knowing the y-intercept and the slope of this line allows calculation of this value right here, which is used for calculation of the surface area. Now, I just mentioned to you adsorption and desorption isotherms, and this is some data that we've taken off of the Bell instrument. This is the Bell Mini, and this was saved data. And what I did was just go over here to File, click Open, and Files drop down, and where I saved it, and then I just clicked on Analysis, and then clicked on this particular adsorption desorption isotherm. You'll notice there are many, many calculations available just by a single click. And by clicking on the adsorption desorption isotherm, this graph was produced showing both the adsorption and the desorption curves. In many cases, people would like to compare various isotherms. And once I've done that, repeated that process, I just went through for one data set and then brought up a second data set to produce this, this overlay. All that's necessary is for me to click on this file here and then drag it over to this location here, and immediately the isotherm for that second material is displayed as part of the graph, and the appropriate index information is presented there as well. In addition, just by clicking, excuse me, by clicking on another area for a spreadsheet, this spreadsheet is just, this is kind of cut off just to be able to present it on a slide. But it shows all the different types of calculations, all the measurement conditions and everything else that's associated with a particular measurement. And that, again, can lead us to having this BET plot. Now, a BET plot, again, it just takes a click to display this information. And what it's showing us here is we have this black line, and this black line is the linearization of the BET calculation. This is the actual BET calculation here, but it's necessary to have as straight a line as possible. It must be as linear as possible. So knowing that the lowest pressure that was used, lowest relative pressure is down at 0.05 at this level here, that is the starting point for us developing this particular line that's used for the final BET surface area measurement. And then one can go over here to the end point, and then by selecting this value here, and in this case this is the point number 14. This is the 14th point in this whole array of values. The whole concept here is to find a point where the correlation coefficient is very, very high. In this case, it's 0.9997, and it means that correlation, the linearization or regression analysis, is providing us with an extremely high identity and correctness. And one other thing to look at when performing BET measurements is the C value. This C value must always be positive. If it's negative, then it does not apply to the BET calculations, and other types of calculations would have to be applied. But ultimately, at the same time, after we've done this, we will find that the surface area value in meters squared per gram, in this case, is 6.9 meters squared per gram. The information that you can get from isotherms is based upon the calculations that are performed. And over here we have the type of information a user would want. You can get the BET method. You can use Langmuir if that's desirable. T-Plot can be very readily calculated, and this is very effective in determining whether micropores or even mesopores are present in the sample. If we get into the go beyond just looking at specific surface area, we can look at pore size distribution, and there are a multitude of calculations that are available. Each one of these is somewhat specific in its use and its application. But one thing to note is that, for instance, these three calculations here are applicable just for measuring or doing an analysis for mesopores. And this is based upon the Kelvin equation and a cylindrical pore model. Now down here, the Innes method, this is for mesopore analysis. And this again is based upon the Kelvin equation, but this is applying to slits that are pores in our materials. But there is a unique thing in the Bell instruments, and that is the NLDFT GCMC calculation. This allows total calculation of all micropores and mesopores that are present, and this is done simultaneously. And that is the calculation that I used previously, where I showed the micropores and the presence of mesopores and some indication of macropores. Getting down to medical dispersion rate, which is important. I'm going to talk a little bit about that application. We can get into the chemical properties. So you have to have some idea as to how to approach and the use of these different calculations to get the best information possible. And we have Bell experts that are well versed in this area that can direct you and assist you in that regard. Now, most of what we've been talking about is Absorption, and Bell has a number of instruments available for that. The Bell Max, which is a kind of a high-end model, its capability is low pressure adsorption. And low pressure, remember, we were at a very, very low pressures when we were looking for our micropores. And it can also do vapor adsorption measurements, such as water or some other types of vapors. The Bell Mini is a device for specific surface area and pore size. It's a low-cost model. It's very high reproducibility, and it's very compact. The nice feature about that is that you can perform 3 measurements simultaneously using the Bell Mini. And then the other Bell instrument, and again, I have to mention there are other Bell instruments that are designed for very specific applications. And the Bell Zorb, this is for monitoring water and other non-corrosive organic vapors, methane, and things of that nature. Well, I mentioned to you Kemahsorption as well as Adsorption. Well, Kemahsorption is very similar to doing a titration in solutions. And if you were to have a solution that has a pH of 10 and you wanted to see what the titration curve would look like, you would start to add a quantity of acid of a known concentration. And as you would add a small amount of the acid to start the titration, some effect would be observed, either a drop in pH, or if you're using an indicator, a color indicator, you may see a color change depending on the type of indicator dye that's used. But there would be some type of a response. But as we start to increase the amount of solution of acid to that base, there would be constant changes along each step of the way as we added more and more of the solution, the acid solution. Well, pulse Kemahsorption is very, very similar to that, in that a given volume of an adsorptive gas is provided to the sample. The sample will then react with that adsorptive gas. And again, this is an irreversible process, and there's a slight delay to allow the chemistry to occur. And then when that is finished, then another amount of the gas is provided, just like we were doing during titration. And then again, there's a slight delay so that the chemicals the gas can react with the surface. And that process continues until there is no more gas involved with the chemical reactions. Just to give you an example of this, in this case we're going to see a pulse 1, 2, 3, 4, 5. And these are 5 additions of the adsorptive gas. Now, this is the total amount of gas that has been applied. Down here, this is the amount of gas that was not adsorbed. So within this yellow region here, this is the amount of gas that is truly adsorbed and reacted with the surface. So then there's another pulse of the chemical, and again, this is the amount that could be adsorbed completely, but this is the amount that is not adsorbed. So this yellow area again represents how much of the gas has been adsorbed. This continues until we reach a point where there's this last 3 peaks represent non-adsorbed gases, and the process and the measurement is complete at that point. Then it's necessary for the instrument just to determine the total amount adsorbed, and that would complete the measurement. But it does allow plenty of time for chemical reactions to occur and to get the best indication of the reaction and how the surface is interacting. One really prime example of this is catalytic converters that are in automobiles. And we know that gas engines produce many compounds, and some of those compounds are various nitrogen oxides, carbon monoxide, and various types of hydrocarbons. And the catalytic converter converts these into less noxious gases, but unfortunately we do have these greenhouse gases, CO2, that is being produced. So there's a reduction reaction as well as an oxidation reaction that occurs inside the catalytic converter, so that what we wind up coming out of our exhaust is carbon dioxide, water, and nitrogen. Now that catalytic converter, there are different types of catalytic converters on the market that are used in automobiles, all with the same basic purpose. But it has a structure that looks something like this. And out here in this white area is a ceramic substrate, a ceramic structure, and that ceramic structure is part of that ceramic structure is that we have an aluminum oxide surface, and to that aluminum oxide surface is bound the reactive metals, platinum, palladium, and there are others as well. And those little round circles represent those particular elements. The whole idea here to test these materials is to determine the metal deposition rate. Metal dispersion rate. And that is the amount of metal that's exposed on the surface divided by the total amount of metal that is available in the total system. Now, the issue here is that we can have these metal constructs, but these pieces of these of the metal structures are embedded inside the alumina and the other parts of the superstructure. And as a result, these molecules, these platinum and palladium atoms, are not available to aid in the conversion of the noxious gases. So it's very important to find out how much of these metals are actually on the surface and available for chemical reaction. So there is a means of doing this by taking a sample of this entire material and measuring the Kemahsorption amount using hydrogen and carbon monoxide. These gases will absorb only to the metal and interact with the metal. So as a result, only a portion of the metals are available. It's important to know how much of that is available as in terms of the quality control of the catalytic converter materials. And again, this is called the metal dispersion rate, and this is a means of determining the availability and the quality and the capability of the catalytic converter to convert noxious to less noxious gases. There are many other metal catalyst applications, some of them involving hydrogen, catalytic reforming of naphthas, methane, methanol, methyl alcohol synthesis through carbon monoxide hydrogenation using nickel. Down here, promotion of oxidation, and it can be epoxidation of ethylene using silver metal, oxidation of ammonia using platinum, gold, and silver, and the oxidation and removal of CO, carbon monoxide, and hydrocarbons using platinum. And there's a whole host of other applications. One of the things I want to point out is that the Bell surface area equipment is designed to be integrated with other types of instrumentation. In this particular case, this instrument here, and this shows a control panel down here with all the valving and activity of the instrument as it goes through the entire process. These lights will illuminate or stop illuminating depending on the process. So the operator can watch the process occur at any stage during the operation, which is very nice because you always know what the instrument is doing and where you are in the measurement process. But this shows a gas chromatograph integrated with what's called the Bell RIA, and this is a microreactor, so the entire reaction can be monitored by using GC and also the Bell surface area. The GC will give the amount of different gases, even gas mixtures that are being proposed and addressed to the sample, the material, if it's a catalytic converter or other type of substrate. And from that, the instrument can monitor the surface area and the effects of what gases are reacting and how well they're reacting in terms of the stoichiometry of the chemistry. So the products for Kemahsorption, and there's some terminology I just want to point out here for Bell products. The TP means that there's a temperature programming. This becomes kind of important when you're looking at catalytic converters because, as we know, when we turn on the engine after a cold night, that engine is not particularly warm, and the catalytic converter may not be operating at its peak performance. But as the temperature increases, then the catalytic converters will operate at those warmer temperatures. So each one of these devices has its own particular name. Starting with TP, we have temperature programming. We can monitor the desorption, reduction reactions, oxidation reactions, and then on top of that we have the pulse, Kemahsorption, and as well a BET measurement. There's a basic model that is compact and it's very affordable, automatic data acquisition and temperature control. Then we start to get into some instruments because of the types of gases that can be proposed to the instrument, where we have automatic temperature control, flow control, but now we start getting into where we might want to be using something like methane or other gas or even a noxious materials such as pyridine that can be used for various types of testing. And Bell has these instruments available to provide for a high level of safety and control over various types of chemicals. There's a high-end model, and each one of these has a greater and greater capability. And then we get to a high throughput model, which is very similar to the Bellcat B, which is the standard model. And this is capable of doing 3 samples simultaneously and provides for a high throughput of sample analysis. And with that, Jason, I'll turn it back over to you, and I'll be glad to answer any questions that you might have.
Thank you, Phil. So now for next steps, if you're interested in sending samples for complementary analysis or scheduling an on-site demo, please send me an email. My email is posted up there, or contact your local rep. Also, we will be posting an archivable version of this presentation so you can view it on demand and share with your colleagues by visiting our SlideShare page. I will also send out the link sometime next week. So now